Hello, good evening. It's me again, Jean-Louis Van Bella. I've done a few lectures. I think my lecture yesterday was a bit of rocket science, I think, in terms of the math you needed to understand what I was talking about, gauge invariance in electromagnetics. I want to do something easier, something very easy actually, and you will say why? Well, the goal is to get more reads of my papers on ResearchGate. I will show a few. They're going quite well, but it's good to be criticized, and you can only get criticized when people actually go through the trouble of reading what I write. I want to talk today a little bit about my worldview, I would say, because ultimately, why am I studying physics and math and quantum field theory? I want to start now. It's ultimately about wanting to know where we came from, where we are going, and then I mean literally, this universe, our planet, the strange thing of this machine in our head, this analytical machine that can appreciate the beauty in these wonderful equations. I'll start with a very simple one to explain that that's sort of a physical interpretation of Einstein's mass-energy equivalence relation. So E is mc square, right? My pen doesn't seem to work. E is mc square. There we go. So what do we have there? We have energy. We have mass, and then we have the velocity of light squared. I think the velocity of light is the easiest thing to understand. Energy and mass itself. It's kind of strange that people tend to forget what they're talking about. What energy do we have in that equation? And mass, what is mass really? So let's start maybe with mass. I think mass ultimately is what I write here. It's the inertia to a change in the state of motion. Motion of what? Well, of a particle. And I will argue we're mainly talking matter particles. And then what are matter particles? I will talk about it in a moment. But that's sort of mass. The inertia to a change in the state of motion. Now you will immediately say that the definition doesn't cover photons, or neutrinos are also like traveling at the speed of light or near the speed of light. That's still not quite clear from experiments. But we have these light particles, and they seem to have zero rest mass, but they have relativistic mass, and so the mass concept should also cover relativistic mass. So something, it's a very strange idea, something that has zero rest mass does not have any inertia, to a change in the state of their motion, and so they must, the slightest force on them will cause them to travel at the speed of light. It will give them infinite acceleration from a mathematical point of view. So we'll leave it in the middle if that's a reality or not. But yeah, light particles, theoretically and practically, as far as we know, they travel at the speed of light. So they have a relativistic mass and therefore also an energy. So the the mass energy equivalence relationship also applies to them. Let me quickly go over that. Actually, if photons have mass, I quickly want to derive the Bray's relation for photons, which, as we know in his paper, he extended to matter particles, the matter wave. So yeah, the photon, the definition of a linear momentum. Light particles, I want to stress that from the start, they're linear oscillations. Linear oscillations of what, you will ask? Well, of a field. What's a field? Well, it's like force without a charge to act on. They don't carry charge. But yeah, as you know, momentum is always mass, in this case entirely relativistic mass, time the velocity, which is c. We can apply a set, and it's a universal mass-energy equivalence relationship. The ESMC square relation to the mass factor, and so we arrived at the momentum, the linear momentum. It's a pushing momentum, really. When Einstein discovered, should be equal to the energy of that photon divided by the speed of light. We then have this one. The Planck-Einstein relation, as it's called, which you can also write in terms of, the reduced version of Planck's constant times omega, which is the linear frequency as we know it, the normal frequency divided by 2 pi, and it gives a frequency in radians expressed in radians, angles, phase. In any case, I'm losing you there if I talk about these things. But if you combine these two, you can see that energy is here h times the frequency divided by c. So you arrive at h. C goes away. So we have indeed that de Bruy's relationship. I'm just noting it how nice these equations all work together, and why you shouldn't look at them in isolation. So let's now go to matter particles. What's matter? Matter is, for me, charge in motion. So to illustrate the example and then get into the discussion, I would say, like with the context of, we talked about the energy here of light particles, which is all relativistic mass. But the energy, when you're gonna look at matter particles, and we're thinking of, what gives them mass? What gives them a rest mass? Well, I must say, well, they have a rest energy. So there must be, and then you talk about energy. Energy is a force over a distance. A Joule is so many newtons times meter. Joule is Newton meter. So you will have this common distinction in physics that, they're just like in any oscillation. So I think we're going to be talking about the oscillation of a charge, naked charge, +1, -1. We know charge is absolutely quantized, and it's either +1 or -1. Well, in natural units, it's so much Coulomb, I forget now. But you will make a common distinction between kinetic energy and potential energy when you're talking about, nodal oscillation of something. Think about what I draw here, like a classical spring, all right? So the mass in the spring, as it goes up and down, will have kinetic energy, but there will be potential energy that is stored in the spring itself. So you can, like motorbikes and engines, so you can also think about a piston, where the piston will have kinetic energy, and inside the cylinder you will have gas that's compressed and expands, and so you have a potential energy in there. What I would like to do you to do now is think of sort of a naked charge. Don't think about particles or whatever. Think about a naked charge, not an electron, because an electron said, I think it has structure, it has a certain size, a radius, an interaction radius when you fire photons at it, and you have this quantum scattering. Think just about a naked charge, and then we will think about it in being in some oscillation. This oscillation will be particular. Think of an oscillation that goes up and down, and also goes sideways. The net result will be that this charge will go round and round and round. So we have two linear oscillations that make up an orbital oscillation, and I think that's the paper I presented in my previous video on the de Bruy's matter wave concept. That's probably the mistake that was made. When we talk about an oscillation, we assign a frequency to an electron or a proton, an elementary particle, then yeah, you don't necessarily need to think about a linear oscillation, or well, we actually do, but you know, we think about it, an oscillation in 2 dimensions, which means that the elementary particle oscillates, you know, or the charge oscillates in, doesn't travel through space, it oscillates in its own space, which, and that own space is the electron itself. And I made yeah, let me go through this one here. A very easy validation, I would say, of my model is if you take that E is mc squared relation, and then indeed you say like, okay, this C is a velocity. Well, think about if the naked charge, just like a photon, would have zero rest mass. It's not a photon, huh? It's a charge. Very, very important to say. But it's like a photon in the sense that it has zero rest mass. That means that, and there, you know, you will say, okay, well, what is this oscillation? Is it sort of an elasticity of space-time? No, we think that the oscillation, as the charge goes round and round, it forms a ring current, and so it creates an electromagnetic field that keeps that ring current in its place. So it's like a perpetuum mobile, and its mass is you know, half of it is the kinetic energy, the relativistic mass that this charge acquires as it goes round and round and round, and the other half of the mass of an electron is the equivalent mass of the energy in the electromagnetic field that this tiny ring current generates. I talked a lot about it in previous videos, and the idea is fairly simple, but you know, you need time to go through it. Let me go through these equations and say like, okay, the energy is mec square, just like for photons. But this time I'm really going to interpret light speed as an orbital velocity, and we know that the orbital velocity of something that goes round and round is equal to the radius of that oscillation times the frequency. 1, 2, 3, 4. Oh, it spins around at incredible speed, of course. And then we have the Planck-Einstein relation, which says the energy is equal to, you know, h times the frequency, or h bar times the reduced frequency. So then you can, you know, replace a by, well, c squared here, by a squared times frequency squared, just frequency squared. And that makes sense because if we're thinking of an oscillation, you know that the energy will be of an oscillation is always proportional to the square of the amplitude and the square of the frequency. So that makes nice. And then you have a factor of proportionality in an oscillation, and this factor of proportionality is the mass factor, which is kind of a neat normal, because what other factor of proportionality would you have? So if you do that substitution, you get ma squared times this frequency squared must be equal, because these two energies must be equal, is h bar times reduced frequency, and you get nicely the radius, the Compton radius of an electron. So we have a small tiny charge, and you know, in my papers I developed the idea that this naked charge inside must also have some tiny little dimension, and it's given by alpha times the Compton radius, the fine structure radius. So I explain that, and it's all kind of consistent, and that's sort of you know, a nice and intuitive interpretation, I think, of well, quantum mechanics. Really, what are particles? We have this dichotomy, matter wave, or wavicles. Well, forget about it. We have charges and we have fields. And the Greek philosopher Heraclitus probably was right. You know, pantare, a charge does not sit still. It whizzes around. It finds a motion, local motion. It's in a local motion. It's called Schrödinger hypothesis, basically. It titters around. Tittering is a German word. It whizzes around, and it whizzes around in a very specific way. It obeys the quantization of nature, which is given by the Planck-Einstein relation, E is h bar times reduced frequency over h. So that's basically my worldview. And now we're going to talk a little bit about why this worldview implies that, a number of modern theories, the gauge theories I talked about, quantum chromodynamics and quantum field theory, why they do not appeal to me. So actually, I only have 3 slides, so this lecture won't last very long. But I already talked about it. So we have energy. What is energy? Well, we have energy in electromagnetic fields. It's kind of said energy is a force over a distance. When we have fields, it's like a little bit of potential energy. There's no charge moving around, but there is energy, and that energy, potential energy, can get transformed in potential energy and kinetic energy. A field will, if the field changes, a charged particle will accelerate or change its state of motion. So we have these matter particles, but I said you really should think of matter particles as being charged oscillations. So basically, my worldview is a bit, and that's the thing is, let me start by the latter here. There's an incredible focus on unstable particles, things that don't have a very long lifetime. And then you think about the particle zoo, which started emerging in the 30s, 40s, and more particles. And then that's the thing, what you have since the 80s are all these virtual, hypothetical, or confined, like quarks, particles. Some of are like bosonic character. Yeah, you compile them on top of each other. Gluons. We have WIMPs. You go to the particle data group, and you can see that, and that's my main complaint about development of quantum mechanics in the last 40, 50 years. They did not succeed in really reducing the complexity of this particle zoo, or real particles that we can see in bubble chambers and coming out of colliders and linear accelerators. We just invented this world of models of particles that we can't directly observe, but that we think are validated by the models that we apply to what happens in a collider. So I'm less interested in that. I think that's what I'm going to talk about. Charge is conserved, and we're having disequilibrium states there, situations that do not respect the Planck-Einstein relation, and that's sort of something I'd rather see. I'd rather see a different math, but I don't have that math. So for the time being, I need to keep studying. The neutron is an interesting one. In my interpretation, I really stick to Rutherford's first interpretation that somehow he observed that 2 protons in a nucleus, you don't see that. There will always be a neutron, so the neutron is like a kind of glue that keeps these protons together. And how can it act as a glue? Well, maybe it has a positive and a negative charge, and this kind of a 3-body problem. I talk about that. The neutron is interesting. It's stable only inside of the nucleus. So yeah, the idea, and I'm going to talk about that in a moment, on matter-antimatter annihilation. It is interesting if you think of the neutron being just a plain combination of a +1 and a -1 charge. And then for me, the only really elementary particles are the electron and the proton and their antimatter counterpart, positron, and an antiproton. So yeah, that's my world for you. Electromagnetic fields, 2 things. We have Maxwell's equations, and Maxwell's equations model continuous fields which respond or drive changes in equally continuous charge densities and currents. Special case is photons. That photons are quantized, and I think a bit of them, and I'm going to talk about that as being a bit different than they're electromagnetic fields, but they're traveling fields. They're like a disturbance in that field, and that disturbance is quantized, and I showed that on the previous page. So that's my bipolar or view of the world. A dichotomy basically between, we have charges that oscillate, and we have fields. So we have charges and fields. And then the thing is, like in higher energy physics, and that's what I want to explore in the coming weeks and months. I did a bit, but I want to do more. Is that valid also in, where we have these experiments where proton and antiproton annihilate each other, and electrons and positrons? We see that happen in nature. Cosmic rays come in, and electron-positron pairs are created. But how exactly? Where does the charge come from? And where does the charge go when, a positron hits an electron in some atomic orbital? So the mainstream answer here is, dichotomy between charges and fields is not valid in high energy. No. So we have what's called the Dirac process. An electron and a positron and electron come together and give two high energy, two gamma rays, and that's it. These charges just vanish. You'll say, well, charge conservation law is observed at the global level. The positive and the negative charge, they add up to 0, and so they vanish. I find that highly unsatisfactory. And then the thing is, what I'm going to show now is a positron and an antiproton and a proton. What happens to them? And that's where I've seen some evolution. Well, there's also photons, high energy photons, and they just evaporate. I want to show you first this one. Can matter be made out of light? Where I talk about, and I really invite you to read this paper. There is this SLAC 144 experiment in Stanford's linear acceleration complex, and I really looked at it, and I find it, it claims to it claims to show the Dirac process where an electron and a positron annihilate. I'm not convinced by the setup, and you can go through this paper, and I invite you. The calorimeters, what happened. These photons seem to have no zero rest mass. They travel very slowly, so that sort of thinks, it's not a real photon. It's not a virtual photon either. It's just not a photon, because it seems to carry the charge. So that experiment doesn't convince me, and it has not been followed up. That's kind of funny. Here I want to show that. This is an article where I look like, why is it actually that there's the experiments with electron-positron collisions? There are very few of them that were done in the 60s, and there's like no conclusive evidence that an electron and positron indeed sort of just yield to photons or more photons. The reverse process Bright-Wheeler is the same. I'd also talk about that in this paper or another paper. Yeah, I have to, like the Bright-Wheeler. The thing is, in this paper, it's a long one, is that I say, like, in nature, where you have plenty of positron-electron annihilation, it always happens in the neighborhood, as they call it, of an atom or a molecule. And they, what standard theory says, well, that's the atom or the molecule, the material, or the crystal lattice in which this annihilation happens. That's there, and that's gonna absorb the the extra energy and kinetic energy. And that's where I'm going, like, maybe the role is a lot larger. I write here about here, and that's the relation they wanna have, that an electron plus some particles yields electron positron pairs out of basically nothing. Let's higher. Oh no, I have the other one. I didn't pull that paper up. Let me do it now. or is it this one? Should be lectures on physics. But 7, yeah, okay. There's an earlier one. Bear with me. I'll find it in just a moment. Yeah, you see my other papers here. All sort of a bit of revolutionary theories. What is it? Charge. Nine. Where's 7? Well, seems to have vanished. It was a 7 where I really analyze, you know, what happens with cosmic rays. You know, they do hit atoms, and then there's a number of processes where, you know, a proton can turn into a neutron, and nuclear force. Here, pair production as a nuclear process. In this paper, yeah, I give you the model, but for pair production, I dig into, you know, these nuclear reactions. That's why I call the paper pair production, matter-antimatter production, or also annihilation. You know, I think the charge must go somewhere, and I'm just going to show you one of these nuclear reactions, you know, the interactions between what happens with protons and neutrons. I said a neutron is stable inside of the nucleus, but Schrödinger said, well, maybe a neutron turns into a proton and it ejects then a positive charge, a negative charge. And I think that's true, that there is a dynamic interaction in the nucleus, not through quarks and gluons, but that offers a much more elegant way to analyze matter-antimatter destruction. Let me look for it here. I'm sorry, I'm so unprepared. But you have these reactions: a neutron decay, an electron capture by a proton, a positron emission by a proton, a positron emission by a proton in a second way with a photon instead of a neutrino. So there's a number of reactions that take place, and I think you know, the fact that you know, positron is gonna, you know, vanish and creates this this high energy, this gamma ray photon is here is I mean, this is just one of the sequences where you can see it here. The photon, you know, the gamma ray, or you know, the proton can turn into a neutron, and that can eject a here is for pair creation, where we have a gamma ray, highly energetic. It interacts with a proton. There's also a neutron comes there, and you know, then we have a neutron. The proton becomes a neutron, absorbs somehow a charge from another proton or whatever in the nucleus, and ejects a positron. And then we have the neutron and a positron. That neutron, I said, is not stable or has some interaction, becomes a proton and has to eject a negative, you know, an electron. And then we have the original positron plus a neutrino. So yeah, I said I've come a bit unprepared. The exact, I should have read it out. The nucleus absorbs the gamma ray photon by this proton neutron for one long. That's what Schrödinger said. And nuclear protons stick together because there's this interaction with the neutron. Neutrons turn into protons, and proton neutrons, and then the charge goes around, and then the nucleus returns to its original state, and that extra neutron is gonna, because it's too much, then it's not the base state of the nucleus of this or that atom, will decay back into a proton while emitting that electron. So the net result is indeed that you sort of get the impression that a gamma ray produces a pair, an electron-positron pair. But as you can see, the charge comes from somewhere. It comes from that nucleus. I think that's a much more elegant way to explain matter-antimatter pair production out of photons than what I refer to as the usual hocus pocus, because that's another thing I want to show. So I looked at sort of papers that talk about, for the moment, there are no electron-positron colliders or experiments. They were carried out in the 60s, and then they quickly moved to proton antiproton. So the LAP, the LEP, became a large hadron collider from CERN, and I went to the website, I think, here, where they also sort of say, well, when an antiproton and a proton come into contact, that's a change. They will annihilate, but they don't produce photons. They annihilate into a range of subatomic particles. And the other thing I want to show here is on this one. It's kind of funny when even the large electron LEP, I don't know what's P is, Large Electron Positron Collider was built in the 80s, early 80s. What they wanted to do and prove is the existence of the Z0 boson and W plus W minus pairs. They never intended it to to confirm that the Dirac process, the two opposite charges can vanish into two pure photons. So these Z0 bosons and W plus W minus bosons were discovered while we're smoking gun physics. They think that the theory of these hypothetical particles is a better theory than any other theory, but they disintegrate into normally stable charged particles, like pions and other stuff. So there's nothing actually on the experimental record that tells me, and I've been looking for a bit, I need to look more, that tells me that this Dirac process, mathematical thing, that matter and antimatter annihilate in pure photons. Charge, there's no evidence, let me repeat it, that charge gets destroyed, so to say. Charges, somehow opposite charges can become plane fields. I argue a lot about it, but I will say, why would this matter? You will say this is sort of like a subtle, reflection in a corner. No, I don't think so. I mean, the reason why I'm interested in it is that the standard model of physics that claims that something like a Dirac or a Bragg-Wheeler process exists, that charge can sort of, two opposite charges can literally vanish, or that, somewhere out of space, two photons or three photons, high energy photons can somehow create a matter, a charge and an anti-charge, a negative and a positive charge. That's bread and butter stuff in the standard model of physics, and as I said, it's not backed up by experimental evidence. Now, the problem with that is that the standard model of physics informs, standard astronomical models. And I'm interested, as I said, in physics because I'm actually even more interested in, like, cosmogenesis, as they call it. Where did our universe start? What was the Big Bang like? What was this quark or gluon soup or high energy stuff that then resulted in the split up of matter and antimatter particles? I have a theory about dark matter as well, but and also then if that isn't clear, if we think like, whoa, in this high energy super charge got created out of fields, and fields charge vanished into fields, that makes a very big difference in terms of how things started and how they evolved, and that also informs then where our universe is going. That, of course, doesn't matter to our life. I'm gonna probably have another 20-30 years left. I'm 55, And this is a bit my retirement project in terms of research, but philosophically and as a human being, and you want to use your brain, and then you see like, whoa, if the standard model of physics doesn't make all that much sense, then these standard theories on the Big Bang, I do believe there was like a high concentration of energy and matter and light and whatever, but the way they just take it for granted that standard model is correct, and then astronomers waste all their time on working with wrong models. That matters. The other thing, and it's a funny one, why this would matter, is I've always been intrigued by a lot of these gurus in the world of physics says basically space time is like foam like, and out of nothing we have these bubbles, and space time is not empty, and it's not continuous. So that's a philosophical question. What I said is that nature is discrete. We have these constants, the charge, positive, negative charge. I don't believe in partial charges. We have a Planck's constant. We have this constant of the permanent speed of light. We have the electric constant, the magnetic constant. They combine to give us a fine structure constant, and it's like a triangle. I'm not going to talk about that, but we have these constants in nature, and everything is quantized. Linear momentum, angular momentum, energy, all these things come out of the equation, and you wonder, like, is motion continuous? How does a charge actually move through space-time? And that's something here I draw, and then you may wonder that, oh wow, for this charge here to move to there, well, there's this trajectory which is given by the electromagnetic field. Do we have like an exchange, because that's what quantum field theory is, of virtual photons that give this charge like a bit of a push? We exchange energy and momentum with the field, and that's sort of how a charge moves through space. I think that's medieval. The idea is here that things move because of some kind of contact force, or virtual particles that ship momentum and energy up and down with interactions from the fields. I think there's no exchange of virtual photons here. This what we have is space is filled with electromagnetic fields, and they determine how a charge is going to move through them. And in terms the motion of the charge, just like in Maxwell's equation, determines how these electromagnetic fields change. And that may or may not be through virtual photons that or sub-Planck oscillations. I think that's a redundant hypothesis. It's just like Maxwell's theory. When it came, it showed that the ether space wasn't filled with some kind of ether or substance that made things move around. No, it's empty space. It's electromagnetic fields, and then if this thing is gonna move, we also have to realize there's a force that's acting on that. So the state of motion of this charge changes, but there's no need for a quantum field theory to do that, because otherwise you're sort of in this philosophical nirvana, I would say, where motion is discrete, space-time is discrete, it's foam-like, everything is filled with energy and we just don't see it, but it manifests itself with these matter-antimatter or charge disappearing and yielding photons, and vice versa. So that's a bit of a passionate discourse, I guess, but I like simplicity, and I do know when I talk like to friends or people who don't know me, these are the questions they ask. Why does your theory matter? Well, I think it matters because it simplifies a lot, and also that's something I want to do. Oh, by the way, I do have a paper on sort of these things. What is gravitation then? For me, gravitation is what Einstein said it was. This. Our universe was probably born in a certain space, and it's ever expanding. It's very interesting. I put here the cosmological constant. There was a Nobel Prize awarded for the fact that it's larger than one. The universe keeps expanding faster and faster, unlike that what we thought, that it would at some point in time go slower and slower and maybe contract again. So we would have like an oscillating in and out. But no, maybe there's other universes around that tear our universe apart. I don't know what it is, but I explore these questions here. I also explore dark matter, but I now wouldn't say it's antimatter. It's sort of like, okay, it's a complicated argument where the electric force has a left or right-handedness. The magnetic field vector and the electric field vector are 90 degrees, not out of phase, but they're orthogonal to each other, and it could be plus or minus 90 degrees. And so in our world, our matter and antimatter world, it's one electromagnetic force. You could think of a force, an electromagnetic force with a different signature, I would say, in terms of the electric and magnetic field vectors. Was minus 90, plus 90. And then beginnings talk about special relativity, and so yeah, that's fun stuff to work on. But as said, for that, I prefer a simpler theory rather than digging into. Okay, that will be it, and I hope I didn't bore you too much. In any case, if I did, you're not listening anymore, and that is fine. If you are listening, please like my videos, and I said my objective is a bit to have more reads. I'm actually this one. I'm happy with this one because it actually I saw that, and that's one of the reasons why I'm doing this. It's it got over 5,000 reads now, and that's not bad at all, and I'm happy with it because I thought, like, okay, it's an unfinished paper. I need to do more research on it, but it's clear that if you got more than 5,000 reads, people, this paper is from 2020. There must be something in it. Pair production as a nuclear process, not in the sense of nuclear force or a strong force or weak force. I don't believe in those things, but yeah, for the other papers on, I think nuclear forces inside of the nucleus are also plain electromagnetic forces, maybe explainable through dipoles that are there. Because you have positive and negative charges, so that's a dipole field, and that's sort of a non-conservative, well, it's conservative field, but it's not a symmetric field. And I write a lot about that, and it attracts some attention, and I'm happy about that because I do think my theory goes back to what Schrödinger, Einstein, not necessarily Dirac, but some great minds thought that somehow young wolves, as they were called, under the leadership of Bohr, tried to invent something really fancy, and nobody knows why. It was probably, well, to attract attention, to also probably, as is clear here, these large investments in LEP and a later Large Hadron. You need a scientific agenda for that, and that's fine. I just think this scientific agenda was maybe has become such a fantasy. I like the Chinese. They're gonna build instead of 22 kilometers in circumference, they're gonna build a collider that is 100 kilometers in circumference, and they're pretty. I looked at the website. They're pretty plain about it. They just want to build the biggest ever thing that yields the highest ever energy, as can accelerate these electron or positrons or protons or hadrons, even to much higher energy levels. I hope they're gonna come up with models that do a bit away with this monopoly, I would say, of the standard model in terms of trying to explain what is happening in high energy physics. Maybe it's an idle hope, but I think that these machines in China are going to come online in the next 5 or 10 years. So I will still be around to observe what is happening there. It's kind of nice because I think also this is a problem in physics, that we are really dependent. You can't replicate these experiments that happen in at CERN or at a Stanford lab. There's only one or two machines, and they specialize in doing what they do. And so it's good that China is rebuilding machines that are going to be even larger and going to repeat these experiments. And hopefully that the Chinese genius will indeed come up with models that finally solve the big questions. And maybe their great grand unified theory will be more sensible than the ones that are being advocated now, supersymmetry theory, WIMPs, and what have you. Okay, that is it. I wish you a very nice weekend here in Brussels. It's Friday evening, and I intend to enjoy the weekend and not be busy with these kind of abstruse theories. Thanks a lot for watching.